Hey guys, so this lesson's called Derivatives of Exponential Functions. So it says now we have learned how to differentiate log functions. Now we're going to look at exponential ones. So the claim is that the derivative of some b to the x function will end up giving you just b to the x times ln of that b. Okay, so a small short proof of that would be that you want to let y equal b of x. And then what we're going to do is we're going to ln both sides. So ln of y equal to ln of b to the x. Okay. I can move the exponent to the front. So I would have ln of y equaling x ln of b. Now, from here, I'm going to use, and I'll just put a note, use implicit differentiation. There we go. Okay, and we'll carry that on here. Okay, so pretty much the derivative of ln of y, right, is 1 over y. But since I'm doing implicitly in terms of x, I got to add on the dy dx, right? Okay, so that will equal, so then for this one, it's just going to end up being, think of ln of b as like a number. So say this was x times 2, right? The derivative of, like, say, 2x is just 2. So the derivative then of ln of bx would just be ln of b, because that's like the constant. Okay. So then what I can do, and I'm not going to tag on a db dx because I'm differentiating this in terms of b. Well, actually, technically, yeah. So because I'm doing that, I don't have to worry about it. Okay, so anyways, so now solving this, I'm just going to multiply both sides by y to get rid of that 1 over y. So I'm going to go like that. And I get that dy dx is going to be y ln of b. And y, we already said in the beginning, we let it equal b to the x, right? So that means that we end up getting that b to the x ln of b. Now, will you ever have to actually do that anywhere on the exam? No, but that's technically the formal proof you'll see in a textbook of how they say that's why the derivative is the way that it is. Okay, so now say we have e to the x. Now, this is a very easy one, but the derivative of e to the x is actually just e to the x. And the proof of it, with the same kind of process, is if, let's see, so if we think of like y equaling b to the x, okay, we know dy dx from our previous thing was just b to the x ln of b, right? So then if we apply the same thing, so then if y is equal to e to the x, based on what we just said, we would get e to the x, right, because our b now is e, b to the x ln of e. But we said before that ln of e is just a 1. So that's why the derivative of e to the x ends up just giving you e to the x, okay? So then it says down here that we also have these derivatives with chain rule, or in conjunction with chain rule. So if you have some b to a function, okay, it's kind of like just like what we did the previous day. It's going to equal b to that function ln of b. But then you still, because of like the chain rule type deal, you still have to multiply by the derivative of that function. So if there's a whole function there, not just an x, that's how you kind of handle it. So then for the exponents, e to the x, the derivative is e to the x. But if you have a function there, it's going to give you e to the f of x, and then you got to times that by f prime of x, or just multiply by the derivative also. Okay, so I'm going to do a bunch of examples with you guys, and then hopefully it like makes sense. Okay, so for A, we have y is equal to 3 to the negative x. So we're going to think of that as like a b to the x kind of scenario, but it looks like we kind of have like a function up here, right? Like it's not just x, it's technically negative 1x. So my dy dx, okay, is going to equal, let's see, so we would do, right, because the derivative of b to the x is b to the x ln of b. So this would just be 3 to the negative x, right? So we keep that the same. Ln of the base, so ln of this base of 3. And then we have to multiply it, since there's a function there, times the derivative of negative x. The derivative of negative x is negative 1. So then all I do is I rewrite this, and how you guys are going to see it is they always put the exponent last when they rewrite it for solutions on multiple choice and stuff. So I would write negative ln of 3 times 3 to the negative x. That's like proper notation. Okay, so then the next one, we have f of x's, and then we have an e to the x type of function, or e to the f of x type function. So we're going to use this kind of method. So f prime of x is going to equal, so it ends up being e to the function times the derivative of that function, okay, which is derivative of negative 2x plus x squared is negative 2 plus 2x. And that would be my final answer. Okay, so then the next one is, let's see, they're saying e cubed ln of x. Now e cubed is actually just a number, right? Like that's a constant, so don't let that confuse you. That's just gonna like come for the ride. Okay, the derivative of ln of x is just 1 over x. So this was kind of like a trick question. So the answer to this is just e to the over x, and that's it. Okay, so then turn the page. Okay, so then the next one, we have like a b to the function type scenario again. Okay, so what that's going to look like, we're going to have y prime being, let's see, it's going to be that b to the function, which is 6 secant of x, times ln of the base of 6, and I'll put it in parentheses, times the derivative of secant of x. So we haven't done the derivative of secant of x in a while, but that derivative is secant of x tan of x. And I'm just going to leave it like that. I'm not going to go another line out. Okay, so then e would then be f prime of x equals, so the derivative of ln. So now you guys are going to see like the ln's and the e's are going to mix together. So ln, again, if there's a function, it's 1 all over the function times the derivative of the function. So this is just going to be 1 all over cosine e to the x. But then you got to times it by the derivative of cosine of e to the x. So that's a chain rule thing. So that's going to give you negative sine of e to the x. And then you got to still multiply it by the derivative of e to the x, which is just e to the x. So I took a line and just kind of simplified all of this. Right, like e to the, I wrote negative e to the x sine of e to the x all over cosine of e to the x on the bottom. So this thing actually gives you negative e to the x tan of e to the x. And that would be the derivative. So then for f, let's see, we have e to a function scenario, right? E to some function. So our rule is, our derivative is of that would be e to the function still times the derivative of the function. So dy dx would equal e cosine cubed x times the derivative of cosine cubed. So maybe up here, just rewrite this differently. This just really means e to the cosine of x cubed, right? Like that's really what it means. So to take the derivative of cosine of x cubed, think of it like chain rule. You put the 3 in the front, keep cosine, or keep the function as is, squared. But then you got to multiply by the derivative of the inside, which is sine of x. And then, again, I just took one line and I rewrote this all better. So you want to put anything with e to the exponent or exponential last when you rewrite it. So I'll take the -3 sine of x cosine squared x, and then it would be e cosine squared x would be my final answer. Okay, and then on G, this is going to be quotient rule. And how you know is you have two functions being divided by each other. So we'll just kind of get right to it. So it's the numerator as is times the derivative of the numerator. So denominator as is, derivative of numerator would be, let's see, we would have 3 to the 2x times ln of 3 times the derivative of that function there, which is a 2, minus this, the numerator as is, times the derivative of the bottom is just a 1, all of that all over the denominator squared. And that simplified would be 2x times 3 to the 2x ln of 3 minus 3 to the 2x all over x squared. There we go. Okay, so then for H, this is product rule. And again, how you know, here's one function being multiplied by another. Okay. So the derivative of G is going to be the first function as is times the derivative of sine of 2x, which is cosine of 2x times 2, plus sine of 2x times the derivative of this. Now the derivative of that's a b to the x scenario. Think of this more as like a 1/2 x there. So that's going to be 5 to the negative x over 2 times ln of 5 times the derivative of this exponent, which is going to give you just -1/2. And I'm not going to go any further with that one. Okay, but that's general idea. Okay, and now what we're going to do is we're going to answer a bunch of questions we already kind of know how to answer. We just never did it with finding derivatives with ease or exponential functions. So, for example, 2, it says, for what value of a is the function y equals e to the ax a solution to this differential equation? Okay, so we kind of had this one on the last one, sort of. What we got to do, since they put a y prime, and a y double prime, I got to find all three of those given this y. So we're going to start with having y equals e to the ax, right? So y prime is what we're going to find first. So the derivative of e to a function is just going to be e of that same function times the derivative of the function. So the derivative of a to the x If a is a constant, it's just times a. So in other words, we get ae to the ax is my first derivative. So then my second derivative, now again, a is a constant. So a just comes down, right? When we take a derivative, that constant doesn't go away. It stays with us. So then the same process happens again. So derivative of e to the a to the x is e a to the x times a again. So in other words, my second derivative is just a squared e a to the x. So now we're going to rewrite that y double prime plus 2y prime plus y equals 0. And I'm going to sub those in, right? Like I'm going to sub this in here, and that in there, and then just kind of solve for a. So I would have a squared e a to the x plus 2ae a to the x, or ax, plus e a x equals 0. Okay, so the easiest thing to do, if you guys notice, they all have e to the ax in it. So I could factor out that GCF, and I'd be left with a squared plus 2a plus 1. And then I can factor. And then I can t-solve. I don't need to do it twice, right? It's the same thing. But this one, e to the ax equaling 0, it's not possible, right? There's no, like, there is a way to get it to be 1. Like an exponent equaling 1 would be if this exponent is 0, but the vice versa isn't true. There's no way for me to get an exponent to equal 0. You got to remember what the e, like any exponential function really quick looks like this, right? So it never actually hits 0. So this is like a no solution scenario. So the only answer then would be a is -1, would be the variable we would want a to be. Okay, so then for example 3 now, they're saying use implicit differentiation on this curve. So they're just it's like something we've done a million times. It's just now we know how to take derivatives with exponents. So the derivative of e to the y, or xy, is first. So when we take the derivative of that, that's going to be a little tricky. So this is a function. So we're thinking of this as e to the f of x. So when I differentiate that, I'm going to get e to the xy, but then I got to times it by the derivative of xy. So the derivative of xy would be x as is, derivative of y is dy dx, plus y as is times the derivative of x. Okay, that was kind of crazy. Derivative of x squared is 2x. All right, we're still doing this in terms of x, so I don't have to do a dy dx or anything. Derivative of y squared is 2y dy dx. And derivative of 10 is 0. Okay. So then I'm just going to simplify all this. I'm going to distribute and write what that would be. So let's see how we get x e xy dy dx plus y e xy plus 2x plus 2y dy dx equals 0. Okay, then I'm going to move everything that doesn't have a dy dx to the right. So that's this and this. And then I'm going to actually write another line, because with these like exponents get like really crazy to try to take shortcuts with. So let's just take a line and actually write what we have. Okay. So that's what we have. So now I can factor out the dy dx, GCF style. I get xe to the xy plus a 2y will equal this side. And then I can just divide it away. Okay, so dy dx will just be that negative 2x minus y e to the xy all over xe to the xy plus 2y. Okay, and that's like an implicit differentiation question. Okay, example 4. Now, example 4 wants us to find all the relative extrema and inflection points. So we know as soon as we hear that, we got to do both the first derivative test and the second derivative test, because that's how we get relative max and mins, and that's how we get inflection points. So I'm just going to write y real quick so it's in front of me. Okay, so we're starting with that with y. There we go, sorry. Okay. So then my y prime, I don't know why this can't focus. Okay. This is going to be a product rule for finding the derivative because we have two different functions we're kind of looking at, that one and that one. So this is going to be x as is times the derivative e to the negative x, which would be e to the negative x times the derivative of negative x, which is 1. And then I keep e to the negative x the same times the derivative of x, which is just 1. And then rewriting that, I would get negative x e to the negative x plus e to the negative x. Okay, so now to solve this, I'm just going to right now tell you guys it's never undefined. It's not. E to the negative x is 1 all over e to the positive x, and it just will never be an undefined value. So we don't really have to worry about that, but y prime equaling 0, we're going to solve for to find some critical points. So negative x e to the negative x plus e to the negative x, we're going to set that equal to 0. So I can factor out e to the negative x, and then I just have negative x plus 1 remaining, and then I t-solve. So there is no solution to e to the negative x, remember? So there's no exponent you can possibly make to make it be a 0. So it's not possible. And if you don't believe me, try it in your calculator or graph that and you'll see what I'm talking about. But like this is like a polynomial too, right? So this is not going to ever be undefined. So, okay, so then this one, then negative x plus 1 equaling 0, I subtract 1, negative x equals negative 1 really just means x equals 1. Okay, so with my first derivative test, you're putting it into the first derivative. Now, when I put 1 in to this derivative, you just have to figure out if it's a positive or negative number. So, I'm just going to, again, guys, give this to you. You could check it right now in a calculator. I don't really have a shortcut for you. You could try subbing it in freehand, but you end up getting that it's positive here, negative here. Okay, so that means that the y was increasing here and then decreasing, which means that we have a relative max there. We're going to actually make it a coordinate. So if I put 1 into y, I would get 1 times e to the negative 1, which is actually just 1 over e. Okay, right, because e to the, you guys get that, right? If I put like 1 e to the negative 1, e to the negative 1 is just 1 over e to the 1, right? Okay, So then that's the first derivative test for relative max or min. So then doing it for the second derivative, okay, it's kind of what I found makes this easier is if you kind of look at it factored and do product rule. I did it like the regular way too, but I found that this made it easier for whatever reason. I don't think you have to do this, but either way, you're going to do product rule with it looking like that. So I just did it this way, and then I just felt like it had less work to do. You'll get the same answer either way. So this is e to the negative x, and then times the derivative of this one is -1, plus this one as is, right? I'm just doing product rule. Derivative of that would be e to the negative x times the derivative of that negative x function, which is just a -1. So I end up getting negative e to the negative x plus negative x plus 1 times negative e to the negative x. And then what I did is they both have an negative e to the negative x. So I factored that out. And then I had 1 plus this term remaining, right? So I took 1 plus that out. And then I just simplified inside the parentheses. And I end up getting just, this is 2, right? Minus x. Okay, so now that I had my second derivative, now I just got to find those critical points. Again, it's not going to be undefined anywhere. I don't really have any fractions. So I just need to find where the second derivative is 0. So if I set negative e to the negative x times 2 minus x equal to 0. Again, this is not possible. Okay, you cannot do that. Like there's no solution. But 2 minus x, if we add x, you get x is just 2. So when you test it in the second derivative, again, I'm just going to give you these values. This ends up being concave down when you check it in the set. So you're putting this, like a test value, like 0, into this. So when you put 0 into this, right, you end up getting -1 times 2, which is negative. And then if you say put 3 in there, right, like this is -3 into this makes it again negative. So that's how I get a positive. So that one you can kind of eyeball and see it. Okay, so in other words, since it goes from to concave down to up, that means there is in fact an inflection point there. And I'm going to give you the actual coordinates. So the actual coordinate on the F would be 2. And then if I put 2 into the original function, this one, I would get 2e to the -2, which is really just 2 all over e squared. And I just left it like that so it was exact. Okay, and then we just have one more question. That's, again, a review type of question. So it says, a particle moves along an x-axis with velocity at time t greater than 0 given by v of t is equal to this function. Okay, the first thing that they ask is us to find the acceleration. So we know that the derivative of velocity is acceleration. So we know that a of t would equal v prime of t. So that would be, if I took the derivative of this, derivative of -1 is nothing. Derivative of this is as if it's e to a function. So that would be e to the 1 minus t times the derivative of 1 minus t, which is actually just -1. So you get negative e to the 1 minus t. So then they want the acceleration at 3. I'm just going to figure out what a of 3 is. So that would be negative e 1 minus 3, or negative e to negative 2, or negative 1 over e squared, because we can't have negative exponents. And that would answer that question. So then they said, is the speed of the particle increasing at t equals 3? Well, we know, first off, if both the velocity and acceleration have the same sign, either they're both positive or both negative, it's the speed is increasing. If one's positive, one's negative, we know it's decreasing. So we already know what the acceleration is at 3. We already know it's less than 0. So we got to just put 3 into v and see what that gives us. So I'm just going to plug it in up there. So that would be like negative 1 plus e to the 1 minus 3, or negative 1 plus e to the negative 2, or negative 1 plus 1 all over e squared. Now, 1 all over e squared, like that's going to be a really, like 1 over a bigger number, right? Like e squared is going to be a bigger number, is like decimal. Like this is a decimal. So negative 1 plus that decimal is still a negative number. Okay, so this is all less than 0. And we already know a of 3, which is that negative 1 over e squared, is also less than 0. So our explanation for this would be the speed of the particle is increasing at t equals 3 because a of 3 and v of 3 have the same sign. Okay, so then C is something we haven't really talked about yet. It wants us to tell them for what values of t is the particle moving to the right and which values of t is it moving to the left, and to justify our answers. So I just want you guys to write this down because we really haven't done it. When you're moving right, what that means is that your velocity is going to be positive. If you're moving left, that means your velocity is going to be negative, okay? So for this one, what we want to do is to figure out where the velocity is like shifting gears pretty much, is we want to figure out our critical points of our function, right? So we want to know like max or min points to where it may have like switched direction from going from like positive to negative, like increasing and then decreasing. So when we think of v of t, okay, back at the top, it's never going to be undefined because we don't have to worry about that being undefined, right? In terms of x's, like it's defined everywhere. So I'm just going to write v of t, never undefined. But I can figure out v of t equaling 0. So that's what I'm going to do first. So negative 1 plus e to the 1 minus t equals 0. Okay, so probably the best way to solve that would be to add 1. Then I know e to the 1 minus t equals 1. How I would solve that is, now people might not think to do this, but I would probably, the easiest way to solve for an exponent is to log both sides. In this case, I'm going to do the natural log. I'm going to ln both sides like that. And that's because ln of e will cancel and you just get that exponent. That's like a rule. And ln of 1 is just 0. So now that I have that, I know that t just has to equal 1, right? Because 1 minus 1 is 0. So if t is 1, this is what I'm looking at. Okay. So they told us, though, that t had to be greater than or equal to 0 in the beginning. So you remember that? They did give us like a little bit of a constraint on this problem. So that means that I can't, like if I sub in a number, I can't go less than 0 with it. I can only fit this in there just because that constraint. So if I were to put like 1/2 into the velocity and like test it, I'm going to tell you guys right now, you end up getting like a plus and a minus when you sub that in. So what that means is that since the velocity is positive, that means that it was moving right in this interval. So like moving right from 0 to 1. And then that means it was moving left. And since they didn't restrain us at all going this way, we'll say from 1 to infinity. Okay, so when it's at 1, we know the velocity is 0, so it's changing directions there. But that's how you figure out where, like, going left or right. So then part D says, at what time is the particle furthest to the right? Meaning, like, where did it move, or where was it the biggest positive number? And the only critical point of this is 1. And since it's changing from positive to negative, that means the original position was like increasing then decreasing. So the velocity then has to be the largest, or like the particle is going to be, so like think of it this way, right? Like, so this is going, and like when the velocity is increasing, that's like the furthest right it's going. Once it hits 1, now it starts switching going left. Like now it's going the other way. So at t equals 1, so we'll say the particle is furthest right at t equals 1 because v of t changes from positive to negative, and t equals 1 is the only critical point of x of t. Okay, if there was like another critical point and it switched again from like positive to negative, then we would have to try something else. But since it's our only critical point and it went increasing up until that point, the velocity did, and then it switched to negative, right? Which means it started moving left. That means that that had to be the spot where it was like the furthest right. Okay, guys, that's it. I know that was a longer lesson, so work on the homework. Okay, thanks.